Okay. So many of the students are asking to express or to explain about the counters. So in the digital logical circuits. So let me tell you about the counter. So counter. Counter is a circuit. It can count the number of digits either in the increment pattern or in the decrement pattern. Once again, a counter is a device which can count the number of digits either in the increment pattern or in the decrement pattern. These counters can be designed by a synchronous counter and asynchronous counter. A synchronous counter is one which is having the common clock pulse, and asynchronous counter is one which is to be having a different clock pulse for the different flip-flops. To design this counter, we require the number of flip-flops. The number of flip-flops can be determined by using the formula of 2 power n is greater than or equal to capital N or capital M. Capital M. This capital N is the mode number of modes. This small n will indicate the number of flip-flops. Number of flip-flops. Number of flip-flops. Required number of flip-flops. For example, if you want to design a counter with a 3-bit counter. So a 3-bit counter will vary from 000, 001, 010, 011. It is 100. It is 101, 110. It is 311. That means it is still varying from 0 to 7. 0 to 7. 0, 1, 2, 3, 4, 5, 6 and 7. A 3-bit counter will vary from 0 to 7 with a 3-bit binary. So let me explain the counter with some example. Suppose if you want to design a mode 5 counter, by using a T flip-flop, we know the state table of the T flip-flop. Because of that, we can easily design that mode 5 counter by using the T flip-flop. Okay. So for example, if we want to design a mode 5 counter by using the T flip-flop, the number of flip-flops required can be determined by using the formula of 2 power n is greater than or equal to capital N. That is 2 power n is greater than or equal to 5 capital N. Capital N is nothing but 5. That is 2 power n is greater than or equal to 5. So this small n can be replaced with numbers 1, 2, 3, 4, etc. For example, n equal to 1. If n equal to 1, that is 2 power 1 will be equal to 2 is greater than or equal to 5 is invalid. For example, n equal to 2, it is 2 square equal to 4 is not greater than or equal to 4. It is also invalid. For example, n equal to 3, it is 2 cube equal to 8 is more than 5. Therefore, it is a value. Therefore, you can say that the number of flip-flops required to design the mode 5 counter are 3. 3 flip-flops are to be required to design the mode 5 counter. So let me design the mode 5 counter by using the 3 flip-flop with the T flip-flop by using T flip-flop. So let me design. So I need to design a mode 5 counter by using T flip-flop. So now the state table of the T flip-flop. The present state is Qn, the next state is Qn plus 1, and the input to the T flip-flop is T. It is 0, 0, it is 0, 1, 1, 0 and 1, 1. In the case of T flip-flop, If the same present and next states are to be the same, the input to the flip-flop is 0. Input to the flip-flop is 0. If the present state and next states are to be different, then the input to the T flip-flop is 1. Input to the T flip-flop is 1. So it is the state table of the T flip-flop. By using this state table, we can draw the, or we can find the truth table of the mod 5 counter. Mod 5 is varying from it is 0 0. Let me, it is 0. It is 1 2 3 4. 1 2 3 4. 1 2 3 4 5. That means mod 5 counter will count only the 5 states. 5 states. And after that, whatever may be the present state, that will not be considered. So after, if the present state is 1, it can move to the next state. If the present state is 2, it can move to the next state. It can move to the next state. It can move to the next state. After 4, that means after the 5th state, it can move to the original state. So 0 to 4, after completion of the 5 states, it will reach to the original state. Original state. So let me design the mod 5 counter by using this T flip-flop. So to that present state, it is to be represented by PS. Maybe the 3 flip-flops, ABC are the 3 flip-flops. Let me, the present state is QC and it is QB and this one is QA. It is the present state. Next state is to be represented by NS. It is QC plus 1, QB plus 1 and QA plus 1 will be the next state. And input to the flip-flop, inputs to the flip-flop, input to the flip-flop may be represented with TC, TB and TE. So this, let me consider the present state and the next state and the input to the flip-flops. If the present state is 0, it is to be 0. The present state is 0. If the present state is 0, next state is 1. Next state is 1. So it may be represented with 0 0. Now we can note down the inputs to this 0 to 0. If the present state is 0, next state is 0, input is 0. And next it is present state 0, next state is also 0, it is 0. Present state is 0, next state is 1. Therefore, present state 0, next state is 1, input is 1. Now, we move to this state. If the present state is 1, and next state is 2. It is 0 1 0. And here also 0 to 0. It is 0 to 1. And this one is 1 to 0. 1 to 0. May be represented with this one is 0 to 0. 0 to 1. 1 to 0. May be represented with 1. Next, let me consider this as the present state. This will be the present state. If this is to be the present state, next state is 3. It is 0 1 0 is the present state. Next state is 3. So here also 0 to 0, 1 to 1 and 0 to 1. So it is the input to this flip-flop. And next, this will be the present state, next state will be the 4. So it is 0 double 1 will be the present state, next state is 4. This is 0 to 1, 1 to 0, 1 to 0. So all the states are to be varying. Next, we will consider this as the present state and next state becomes to be 0. So it is 1 double 0, next state is 0 0. So here 1 to 0, 0 to 0, 0 to 0. 1 to 0 is 1, 0 to 0 will be the 0. Now we have completed all the 5 states. More 5 counter states are to be completed. So this 3-bit binary will vary from 0 to 7. 0, 1, 2, 3, 4. And this is 5. And this one is 6. And this is 7. Okay. So after the 5 states, whatever may be the present state, the next states are not to be required. they may be represented with x. The next states are not to be required. If the next states with the present set are not to be determined, the inputs are also to be not determined, unknown. So these are the unknown inputs. Now, by using these present states and the next states, we can determine the input to TC, TB, TA by using the K-map. By using the K-map, determine the input to TC and TB and TA. It is a 3-bit binary varying from 0 to 7. We know that it is a 2 cube equal to 8. 8 cell K-map is to be used to determine the values of inputs TB, TC and TA. So let me use the 8 cell K-map to determine TC, TB and TA. So first K-map for TC. K-map for TC. It is a 3-bit binary. Therefore, 2 cube will be equal to 8 cell K-map is to be used. So here the variables are QC, QB and QA. It is QC and this one is QB, QA. May be represented with it is QC bar and it is QC. It is QB bar, QA bar, and this one is QB bar, QA, and this one is QB, QA, and this one is QB, QA bar. 0, 0, 0, 1, 1, 1, 0 and 1. It is 0 and 1. So I know that it is 0, 1, 2, 3, 4, 5, 6, 7. Now, this is 0, this one is 1, this is 2, 3, 4, 5, 6, 7. This is 0. We are representing for TC. K-map for TC. So 0 is to be placed with 0, and 1 is to be placed with 0, 2 is to be placed with 0, 3 with 1, 4 with 1, 5, 6, 7 are to be with x. So 0 with 0, and 1 with 0, 2 with 0, 3 with 1, 4 with 1, 5, 6, 7 are with x. Now the mapping can be done. If all the cells are to be filled with a unique number, that can be grouped as a single function. Functional value will be equal to 1. All are not possible. We will go with the 4 cells. If it is not possible, 2 cells. If it is not possible, the lower is 1 cell. Here 4 cells are to be possible. By considering this x will be equal to 1. So this by considering this as 1, it is the first grouping. Another grouping also possible. This is the second grouping. Therefore, first grouping function can be written by moving horizontal it is QC, and by moving vertical it is 1. And the second grouping function can be written by moving horizontal it is QC bar plus QC equal to 1. Vertical it is QB, QA. Therefore, the input to TC will be equal to the input to the TC. Input to TC will be equal to QB, QA plus QC. So it is the input to C flip-flop T input. And similarly, we can find the input to TB and TA. So K map for TB. So it is also to be determined. So it is QC, this is QB and QA. It is QB bar, QA bar. It is QB, QA bar 0, 0, 0, 1. And it is QB, QA. And this one is QB, QA bar. This is QC bar and QC. So it is 0, 1, 2, 3, 4, 5, 6, 7. So it is 0 and this one is 1, 2, 3, 4, 5, 6, 7 are 0. X 0 with 0, 1 with 1, 2 with 0 and 3 with 1 and 4 with 0 and remaining are x 5, 6, 7. So here this can be grouped. So it can be grouped. So by grouping this, you can express a single function. So that functional value can be written horizontally it is 1, vertically the common letter is QA. Therefore, input to TA will be equal to QA. And similarly, we can find the K map for TA. So we can find the value of TA by representing in the same representation. So this is K map. It is QC and this one is QB, QA. It is QC bar and this is QC. It is QB bar, QA bar, 0, 0, 0, 1, QB bar, QA. It is QB, QA and this one is QB, QA bar. It is 0, 1, 2, 3, 4, 5, 6, 7. So here also it is 0, it is 0, 1, 2, 3, 4, 5, 6, 7. 0 is 1, 1 with 1, 2 with 1, 3 with 1, 4 with 0, remaining are 0. So 4 with 0, 5, 6, 7 and remaining are to be placed with 1. Therefore, here it is a single grouping. It is a single grouping. So this can be grouped and the functional value can be represented with QC bar. Functional value can be represented with QC bar. Therefore, the value of TA will be equal to QC bar. It is QC bar. So these are the inputs of the flip-flops of a 3-bit binary. Now you can draw the counter by using a synchronous counter. You can draw the synchronous counter with these 3 flip-flops. Let it be flip-flop A. This is flip-flop A. It is A flip-flop having the input of TA and this is QA. And this one is the B flip-flop. Flip-flop B. This is B. And this will be represented with TV and this is QB. And this is C flip-flop having the TC, let it be this is TC and this one is QC. If the synchronous counter is to be used, the same clock pulse is to apply. Clock pulse is to be applied. It is the same clock pulse. It is the same clock pulse is to apply to all the flip-flop. Here, TA equal to QC bar. It is QC and this one is QC bar. This will be taken and this will be connected to this yone. So let me take this as QC bar, QC bar. Otherwise, you have to take this from this terminal and this will be connected to this yone. So this will be connected to this as the input to this TA. Next, TV. This TV. TV equal to QA. So it is QA. And TC with QA, QB plus QC. This one is QA. Let me take this as QA. And this one is TV. Let me take this as QB. These two are to be multiplied. So this QA and QB are to be multiplied. Use one AND gate. This is QA and this one is QB. It is QA, QB. And plus QC. So one more TC is there, QC is there. Let me take this. This is QC. Finally, these two are to be added. Use one OR gate. So it is a OR gate. This output will be connected as the input to this. So it is a TC. So it is a way. The design of mode 5 counter. Similarly, we can design any number of counter by finding the number of flip-flops with the formula of 2 power n is greater than or equal to capital N. Okay.